All right, today we're going to be talking about how to solve circular motion problems for a uniform circular motion unit. So the first thing we need to talk about is the centripetal force equation. Now, we have here is Fc is equal to mv squared over r. It's important to note that the centripetal force is not a new type of force. I understand that it has a new subscript, but it really is just a different name for the net force. So it's just the net force, but it's specific for objects that are undergoing uniform circular motion. Additionally, for centripetal force problems, the only forces that we will include for the net force to make our centripetal force are the forces that point along the plane or along the direction of the radius of the circle. And I'll talk more about that as we go through these example problems. All right, so if you saw my post-lab video about uniform circular motion, we've got these 6 ideas that are true about objects that are undergoing uniform circular motion. So we have the system where the object moves at a constant speed. The system's velocity is not constant. And these first two can coexist by remembering that velocity is a vector, so it has direction also. So it's not that the number or the value of the velocity is changing, it's more that it's the direction of the velocity that changes. Third thing is that the system's velocity is always tangent to the circle. The fourth thing is that since its velocity is changing, it is accelerating, and that acceleration points towards the center of the circle. And the reason is because the forces are unbalanced. So that's number 5. And number 6 is because they're unbalanced, and it's that the winning or the force that's longest that's causing the acceleration points towards the center of the circle. All right, so for our first example, we've got a 10 kilogram ball is tied to a string and whirled around in a circle above this person's head. The ball travels with a velocity of 2 meters per second, and the string is 1 centimeter long. What is the tension in the string? All right, so first up, we want to take a look at what's happening here from the top. So here we've got a bird's eye view of what's happening. I'm not going to draw the person, but we've also got here at the right a force diagram for the ball here. And here's the center of the circle. And if we take a look at the force diagram, we only have one force that we can see if we look down at the person swinging this ball around. And we have the force of tension here. Notice that gravity doesn't show up. Yes, it has mass, but gravity really points into the screen here, right? Because we are looking at it from the top view. Okay, so let's keep that in mind. First up, we have a mass, and that's 10 kilograms. We've got a velocity, that's 2 meters per second. And we've got the length of the string, which tells us the radius of the circle, which is just 1 meter. So just taking a look at this, we can kind of tell that we can solve for the centripetal force acting on the ball. So centripetal force is mv squared over r. We have 10 kilograms times 2 meters per second, and we're squaring only the velocity over 1 meter for the radius. That turns out to give us 40 newtons. So that's the centripetal force. Now, the problem's asking for the tension. Now, the thing is that the tension points towards the center of the circle. There are no other forces that point along the radius. So when we solve for the centripetal force, what we're actually solving for is the force of tension. And that's already done for us. And there's a simple example of circular motion for this case. Now, when we do more complicated problems, we have to make sure that we talk about signs, because circles are different than previous units in terms of direction, because it was very black and white in unit 5 and 4. If we saw a force that pointed to the right, we knew to treat that as a positive. If we saw a force that pointed left, we knew that was negative. Same with up and down. Now, in a circle, everything's always changing, so we need to be able to talk about our sign conventions, or our rules for signs. So here, what we want to do is, we'll just take any circle, and let's say an object's traveling around the circle. Any force that points towards the center of the circle must be treated like it's positive. So it doesn't matter where in the circle, but when we set up our equations, these are all positive. And any force that points away from the center, those have to be treated as negative. So when we set up our equations, you have to remember to stick a negative sign in front of those forces. So the example that we'll do next has to do with one of these cases where it's more complicated. All right, so we are back with our dinosaurs on a Ferris wheel. Here we have the 4 dinosaurs, each with a mass of 100 kilograms. And each dinosaur travels with a velocity of 1.5 meters per second around in that Ferris wheel, which has a radius of 15 meters. And we want to determine the normal force, so the Fn at the top of the ride, and we want to determine the normal force for the dinosaur at the bottom of the ride. First thing, it looks like we have the variables that we need to solve for the centripetal force. So if we do that, we find that the centripetal force is equal to mv squared over r, and we get 100 kilograms times 1.5 meters per second, and we're squaring only the velocity, over a radius of 15 meters. This will give us a centripetal force of 15 newtons. I'm going to circle that. That's not our final answer, but that's what we are going to use when we solve for a problem. Now, the other thing that we can solve for is the force of gravity on each dinosaur. So force of gravity is 9.8 newtons per kilogram times the mass, and each dinosaur has a mass of 100 kilograms. This turns out to be 980 newtons. I'm going to circle it. Not the answer, but we're going to need it later. So at the top of the path, let's take a look at the top dinosaur. At the top, the trajectory looks like this for that top dinosaur, and I'm going to draw kind of a informal force diagram. I'm going to leave off the on by notation because it might get messy here. We've got the force of gravity acting on that top dinosaur, and we've also got a normal force that points upwards. Now I'm exaggerating this by a lot, but I just want to show that the longest force has to always be the one that points towards the center of the circle. So in this case, it's the force of gravity. So if you saw my post-lab video for circular motion, I kind of go into that in more detail. Now, at the bottom, for the dinosaur at the bottom, we have our trajectory still. And this time, I'm going to draw in blue for this dinosaur here. This dinosaur has the same mass as his friend, so I'm going to draw the force of gravity the same length. However, At the bottom, it's the normal force that points towards the center of the circle. So keep in mind that the center of the circle is here for this dinosaur and here for that dinosaur. So when I do this, I want to make sure that I draw the normal force much longer than the force of gravity. So it's true when you're on a Ferris wheel, you feel less normal force on you at the top and more normal force on you at the bottom. And we'll talk about more examples of that sensation in class. Now, to what I was saying about signs, here I have, let's make a net force equation. So again, the net force is just the centripetal force. So the net force or centripetal force is equal to the sum of the forces. Now in unit 5, in our unbalanced forces unit, I would always say it's right minus left, or it's up minus down. For our circular motion unit, what we are going to do is in minus out. The force of gravity points in, and that's the one that gets a plus sign, and Fn is the one that points out, so that gets a minus sign. And likewise, we can do the same thing with this one. Here, our net force is equal to in minus out. So for the bottom, the force that points in is the normal force, because that gets the plus sign, minus the force of gravity here. So that gets a minus sign because it points away from the center of the circle. So luckily we've already solved for the things that we have, and all we have to do is do some algebra to solve for the normal force. So the centripetal force is the same for both dinosaurs, actually all 4 of them. Here it's 15 newtons is equal to 980 newtons minus the normal force. So when we move things around, we get a normal force of 965 newtons. And that should be reasonable because the force of gravity here is 980. What the centripetal force tells us is that it tells us how much the inside force is winning by. So if we check and make sure, if we see that the force of gravity is exactly 15 newtons longer than the normal force. And for the dinosaur at the bottom, we should find that the normal force is 15 newtons longer than this 980 force of gravity here. So in this case, we have the centripetal force is still 15 newtons. I want the normal force, and my force of gravity is still 980 newtons. Moving things around, I have a normal force of 995 newtons for the dinosaur at the bottom. So after this, we're going to pause and make sure and see if that's reasonable, and it looks like it is. 995 minus 980, the difference of that is 15. So the force that points towards the center is greater by 15 newtons. So here's a more complicated example, and to be honest, this is as complicated as we will get for this unit. So if you're able to understand this one, you should be good to go with a little bit more practice, and we'll talk more later.